We now start our discussion on chapter 6 module 1. We have already seen in the last chapter that we can define the Lebesgue integral of bounded functions defined on sets of finite Lebesgue measure, and we have also seen that it is advantageous than the process of Riemann integration. Now, in this module we will continue that examination. Now, the first thing which comes to our mind is that we have already defined the Lebesgue integrability of bounded functions, but can we define it for unbounded functions? So, on this point we start our first slide of this module. Consider a function like g, where the function g from closed 0 1 to r is defined by g x equal to n when x equal to 1 over n and 0 elsewhere. Now, if we consider this function, there are countable number of vertical lines in closed 0 1. As in the case of chi q, the only difference is that as n becomes large and large, the height of the vertical lines become larger and larger, but still there are only countable number of vertical lines. So, they cannot make a region of positive area, but still this function we know that it is not Riemann integrable, but we will see that this function is obviously Lebesgue integrable. So, we start again with the basic notion of a non-negative simple function and define its Lebesgue integral. We have already defined the Lebesgue integral of a simple function, but here we are taking a non-negative simple function first. So, if S is a non-negative simple function defined on a measurable set E, and if alpha 1, alpha 2, alpha n are the n distinct values of S, then as before the canonical representation of S is given by S equal to sigma I is equal to 1 to n alpha I chi E I, where E I is the set of all those points x belonging to the set E, where S x equal to alpha I. And just as before, we can define integral over E S d mu equal to sigma I is equal to 1 to n alpha I into mu E I. The only difference from the earlier definition is that in the earlier definition we had taken a measurable set E of finite Lebesgue measure. Here the Lebesgue measure of E can be infinity. So, calculating the value of the Lebesgue integral, we can have some terms like 1 into infinity or 2 into infinity, or for that matter 0 into infinity. And to avoid that, we take the convention that 0 into infinity is equal to 0. So, see that the value of this integral always exists, it is greater or equal to 0, but here the value of the integral can be equal to infinity. We have a very useful observation now, that if S is a non-negative simple function defined on a measurable set E, then the set function nu defined in this way, that if we define nu of A as integral of S over the set A, this set function becomes again a measure on ME, which is the collection of all measurable subsets of E. That is, nu is non-negative, countably additive, and nu phi is equal to 0. See that if we take S as the constant function 1, then we get back the Lebesgue measure mu. Otherwise, we get different measures. Again, we go back to the convergence theorems. We again recall one example which was given earlier, but we will look at the example from another viewpoint. Let Fn be defined on closed 0 1 as follows. Fnx is equal to 1 if x is equal to R1, R2 or Rn, and 0 otherwise, where Rn n belonging to n is the sequence of rational numbers in closed 0 1. Note that this sequence of functions Fn is monotonically increasing, that is, f1 is less or equal to f2, less or equal to f3, etc. And we already know that each function Fn having only a finite number of discontinuities in closed 0 1 is Riemann integrable. We know that this sequence Fn converges to the function chi q in closed 0 1, which is again not Riemann integrable. And on this point, we will present one of the most well known convergence theorems of Lebesgue integration, which is known as the monotone convergence theorem. Let Fn be a sequence of measurable functions defined on a measurable set E, and we take the sequence Fn as monotonically increasing, that is 0 less or equal to f1, less or equal to f2, less or equal to etc., less or equal to Fn, less or equal to Fn plus 1. So, all the functions are non-negative. We also assume that this sequence Fn is pointwise convergent to the function f, that is, limit n Fnx equal to Fx for all x belonging to E. Then the conclusion of the monotone convergence theorem is that the limit function f should be measurable, and again the Lebesgue integral of f over E is obtained as the limit of the integrals Fn over E, that is, limit n integral over E Fn d mu is equal to integral over E f d mu. We start the proof. Since each Fn is measurable and by our assumption the sequence Fn converges pointwise to the function f, so f should also be measurable. Again, since the sequence is monotonically increasing, that is, for all n, Fn is less or equal to Fn plus 1, and this implies that integral of Fn d mu should be less or equal to integral of Fn plus 1 d mu, since we are taking the integral over the same set, and this is true for all n. So, if we consider the sequence of the values of the integrals, integral Fn over E d mu, this is a monotonically increasing sequence of real numbers, and we know that a sequence of real numbers, if it is monotonically increasing, then its limit always exists, either it is equal to infinity or it is equal to a finite number. So, limit n integral over E f n d mu always exists. Now, if the limit is infinity, then actually there is nothing to prove. So, we will prove only the case when the limit is finite. So, suppose that limit n integral f n d mu over E, this limit is equal to the real number alpha. Observe that since f n is less or equal to f, because we know that for a monotonically increasing sequence of real numbers, its limit is the supremum of those real numbers. So, f x is always greater or equal to f n x for all x. So, f n is less or equal to f for all n, and so integral f n d mu over E, this is less or equal to integral f d mu over E, and this is true for all n. So, taking limit n tends to infinity on the left hand side, we have this inequality that alpha should be less or equal to integral f d mu over E. So, we have obtained one part of the equality. We now have to show the other part of the inequality, that is, we now have to show that integral f d mu over E is also less or equal to alpha. Now, to prove the reverse inequality, let us take any simple function s defined on E with 0 less or equal to s less or equal to f. Recall from the last chapter that since f is a non-negative function, so the integral of f is obtained as the supremum of all integrals s d mu over E. Let 0 less than c less than 1 a number. Define a set A n in this way. A n is taken as the collection of all those points x belonging to E, where f n x is greater than C s x. Now, see that s is less or equal to f. So, s x is less or equal to f x, and since c is less than 1, so C s x is strictly less than f x, which is the supremum of f n x. Now, since each f n is measurable, also s being a simple function is measurable, and so C s is also measurable, we can show that these types of sets where f n x is greater than C s x, these sets are also measurable. And since the sequence f n is non-decreasing, so it follows that the sets A n have this property that A 1 subset of A 2, subset of A 3, subset of A n, subset of A n plus 1. So, A n is a increasing sequence of measurable sets. We first show that the union of these sets A n, which is equal to limit n A n, this turns out to be the whole set E. Let x belongs to E. Now, see that if at the point x the value of f x is 0, then the value of C s x is also 0. But we know that f1x is greater or equal to 0. So, f1x is greater or equal to CSX, and so x belongs to the set A1. If fx is greater than 0, then CSX is also strictly greater than 0, but CSX is less than fx, which is the supremum of fnx. So, from the definition of supremum, we can find a positive integer k for which kx is greater than CSX, and subsequently the point x belongs to the set AK. So, this shows that every point of the set E belongs to some of the sets AN, and so union of all these AN is equal to the whole set E. See that if we consider the integral of Fn over the whole set E, since AN is a subset of E, so this is greater or equal to integral of Fn over AN. This is again greater or equal to integral of Cs over AN, because on the set AN we already have Fnx greater or equal to Csx. But we know that integral over AN Cs d mu, this is equal to C integral over AN S d mu. We have already seen that for a non-negative simple function S, this particular integral defines a measure. So, if we take n tends to infinity in the above inequality, then we get the following. On the left hand side, we have the limit alpha. So, alpha is equal to limit n integral over E Fn d mu. This is greater or equal to C integral over E S d mu, because the sets AN are monotonically increasing and their union is E, and we know that the Lebesgue measure is continuous from below. Now, this above equation, this is true for any C for 0 less than C less than 1. So, if we take C closer and closer to 1, then we get the following. Alpha should be greater or equal to integral S d mu over E. But recall that we had taken any arbitrary non-negative simple function S less or equal to f. So, this particular inequality is true for all non-negative simple functions S which are less or equal to f. So, if we take the supremum on the right hand side, we get alpha should be greater or equal to integral f d mu over E. And we already have observed that alpha is less or equal to integral f d mu over E. So, we have the equality that alpha should be equal to integral f d mu over E. We finish our discussion on the module 1 of chapter 6 here. So, what we did in this module is that we have defined the Lebesgue integral of non-negative measurable functions on arbitrary measurable sets, and we have proved a very important convergence theorem, which is monotone convergence theorem.